Ramanujan for G is now available on the Google Play Store. Try it out for free.
So, good morning, students. In our last class, we have studied about some important compounds of boron, and particularly we have started p block elements. And p block elements, group 13 elements, we have studied particularly. And there that's what I was saying. We studied about borax, some important compounds, and orthoboric acid, also known as boric acid, and diboron, and some other important things about this group 13 elements. And later on, we finish that portion. Now we are going to start group 14 elements or carbon family or tetrails. So group 14 elements are also called carbon family, or they are also called tetrails. Tetrails, the spelling that you can see here, and group 14 contains these elements. These elements: carbon, silicon, germanium, tin, lead, and flerovium. So you can see 6 elements here. So from carbon to flerovium, flerovium is the recently included element, and this element is actually, it is a radioactive element. It has a very short lifetime. And so the carbon, silicon, germanium, tin, lead, I hope you can remember their name. From the symbol itself you can recognize carbon, silicon, germanium. Up to here it is very clear. This is tin, stannum, that the symbol comes from the Latin name, and the Pb for the lead. So tin and lead, and the flerovium, Fl. These are the members of group 14 elements. Carbon is the 17th most abundant element by mass in the Earth's crust. So carbon on the Earth's crust is one of the most abundant element. It's the 17th most abundant element. 17th, you can understand, this means that there are 16 elements which abundance on Earth's crust is more than the carbon. And this carbon is widely distributed in nature in free form as well as in the combined state. So free form and as well as in the combined state, it means the carbon can exist in the elemental form, and in elemental form it exists in the form of coal, graphite, and diamond. And in the combined state, it mostly exists as the metal carbonate or the hydrocarbons, carbon dioxide gas, or the carbon monoxide in some small amount. And all the living forms that you see, all the living forms, they mostly contain, major part of their body contains organic molecules, whether protein, whether DNA, RNA, or any the mm, plasma membrane, or any other sort of membrane that you look about any cell organelles or the any organism. But we will see it, you will see that the most part of this living form is a organic compound, other than bones mostly contains inorganic compounds, and bones also contains protein, and those proteins contain carbon. And we will see later on what is the basic structure of protein and other biomolecules. The carbohydrate that we eat, and everything contains carbon. So these compounds also contain carbon. So carbon is there in a large amount in living forms, and that's why without carbon, living forms cannot exist. And so the chemistry of carbon and the carbon family, since it is found in, it has been started, its understanding started because the people have found that they exist mostly in organisms, living forms. So the chemistry of carbon we also call organic chemistry. The word itself came from the organism. You can see organic chemistry. So carbon is the most versatile element known to humans. Its combination with other elements such as dihydrogen, dioxygen, chlorine, and sulfur provides a number of materials ranging from living tissues to drugs and plastics. So plastics, mostly polythene, that you know, it's a polymer of ethene, and ethene is an organic compound. The carbon content compound its formula is C2H4. And so almost all of the polythenes, all kinds of plastic, it contains carbon. So carbon is also there in the materials, and as well as most of the drugs also contains carbon. So they are mostly organic compounds, plastic, and all that we know. Organic chemistry is devoted to carbon containing compounds. It is an essential constituent of all living organisms, as I explained earlier. So naturally occurring carbon contains two stable isotopes. So about isotopes that we know, for a particular element, if there are many different types of atoms for a particular element, not atoms. If the masses may you can call more appropriately. The types of atoms are of the same type because type of atom is determined based on the number of protons that is there into the nucleus. And so carbon, if it is carbon, it will always have 6 electrons in the 6 protons in the nucleus. However, we see the number of neutrons in nucleus may vary for different atoms, and based on that isotopes are determined. So having the carbon has two naturally occurring isotopes which are stable, and these are carbon 12 and carbon 13. So this we also write carbon dash 12 or carbon dash 13, right, or 12 as a left superscript or 13 as a left superscript. This is another way of representation of isotopes that is shown here. Another way is what I said, carbon, you can write carbon, then dash 12 or C dash 12 you can also write. So these carbon 12 and carbon 13 are, they are stable, they are not radioactive. However, carbon 14 also exists and it is radioactive. Carbon 14 is also naturally occurring isotope which is radioactive, carbon 14, and radioactive with half life 5770 years, 170 years, and it is used for radiocarbon dating. Particularly, suppose if you know some fossils or something in a given range, to find out the age of the fossil, we actually use the radiocarbon dating. The silicon is and the fossil also, if the fossil is living form, it's a organs, some portion of this organ, if it exists there. Otherwise, if the fossil is very old, then we resort for some other kind of dating. But if the fossil is not very old, then we use radiocarbon dating. Silicon is the second most abundant element on the Earth's crust, and on the Earth's crust, its percentage abundance is around 27.7% by mass. However, on Earth, because Earth also contains elements on in the atmosphere, not only the elements in the crust, Earth's crust. So, on entire Earth, on the planet, if you see the percentage abundance of silicon, it would be around 25%. So that's why it's the second most abundant element after oxygen on the Earth's crust, and is present in nature in the form of silica and silicates. Silica is the sand that you know, and about the silicates we will study it later. So silicon is very important component of ceramics, glass, and cements. These are things that we know. Perhaps you also know the ceramics, glass, and cement. They contain silicon. Germanium exists only in traces, means in a very small amount germanium exists on Earth. Ultra pure form of now all the elements that we know, the silicon and germanium. So ultra pure form of silicon and germanium are used to make transistors and semiconductor devices. They are actually silicon and germanium are semiconductors, so they are used to make semiconductor devices or the transistors where we use semiconductors. So silicon tin occurs mainly in cassiterite as this is as SnO2. So tin exists in the form of cassiterite, means SnO2, which we call cassiterite, or, or the mineral, and lead occurs as galena, lead sulfide, PbS. Ferrovium is synthetically prepared radioactive element. Fleromium has been prepared only in a small amount, and because it exists because of the radio, people, it's artificial element. People have prepared it in laboratory. So its half-life is short and its chemistry has not been established yet because of various short half-life of the most stable isotope of fleromium also has a very short half-life, and because of that its chemistry has not been established yet. Chemistry means its reactions, its properties, physical and chemical properties have yet not been determined. Let's look into the general properties of group 14 elements. Let's first see the electronic configuration, and group 14 elements, as we know, the carbon, silicon, germanium, tin, and lead. Fleromium we will not study about because other than electronic configuration, so definitely we can write. Other than that, its other properties are not known. For the fleromium, they are not determined, they are not measured, so that's not important for us to study about. So the outermost electronic configuration of these elements is NH2NP2. The general electronic configuration is NH2NP2. for all the elements that are there in group 14 or the carbon family. If you look at the electronic configuration of all the elements one by one in the step, so carbon is what? Helium, electronic configuration of helium, then 2s2, 2p2. It helium electronic configuration of helium is 1s2, so electronic configuration in detail electronic configuration of carbon is 1s2, 2s2, 2p2. And when 1s2, 2s2, 2p6, it is the electronic configuration of neon. So electronic configuration of silicon, one can write electronic configuration of neon, and beyond that 3s2, 3p2. So what do we see here? The core of carbon is the core of is the has the electronic configuration of helium, means 1s2, and core of neon also contains electrons in only s and p orbitals. Two here, 1s2, 2s2, 2p6. And then the valence shell electrons will be there, 3s2, 3p2. So the total number of electrons from the electronic configuration one can find out as a total number of electrons in the valence shell as 4, 2 electrons in s orbital and 2 electrons in p orbitals. And so total number of electrons are 4, and since maximum total number of electrons in the valence shell are 4, so these elements, the group 14 elements, can show maximum valency up to +4, the covalence of the oxidation state up to +4. And since electrons number of total number of electrons are 4, so this 4 minus 8, that lowest oxidation state these elements can show is 4 minus 8, that is -4. So any of the elements that can show minimum oxidation or lowest oxidation state, the minimum covalency is -4. Now covalency one cannot say minus, so oxidation state is -4. Covalency would be 4 only. So inner core of these elements in this group differs similarly to group 13 elements, and this group 13 elements I have explained earlier. So what does it mean? The core of these elements do not contain any d electron. You can see here, from here argon, germanium, and the electronic configuration of argon up to here there is no d electron. So d electron also, this core contains, core of germanium also contain d electrons. So electronic configuration of argon plus 3d10. So electronic configuration of argon is what? 1s2, 2s2, 2p2, 3, 2p6, 3s2, 3p6. Electronic configuration of argon, then 3d10, and later on this. So these electrons, 4 electrons, are valence shell electrons. And then tin also contains, you can see here, from here the f orbitals will also be available, and so no, sorry, tin also contains only d electrons, as you can see here. And although vacant f orbitals will be available, but electrons are not going there, so electrons will start filling only after that. And so lead and even the flerovium contains electrons in f orbitals. So the core differs a lot in this group 14 elements. Why? Because this core of carbon contains only electrons in s orbital. Core of silicon contains has electrons in s and p orbitals. Germanium and tin had electrons in s, p, and d orbitals. Lead and flerovium will have electrons, core electrons will have s, p, d, and f orbitals. They all involved. They all involved there. Now let's look into the covalent radius. Mostly what is important for us is to see the trends. And here the trend, what we see here, the 2s2, 2p2, that's the outermost shell electronic configuration, and rest of all the orbitals are completely filled. Only these orbital, p orbitals, being completely filled. Up to you can see all the orbitals other than p orbital, outermost p orbital, all the other orbitals are completely filled when we see the electronic configuration. Now look into the covalent radius. Covalent radius, when we see here on this table, and see carbon 77 picometer, and from carbon to silicon we see a very large increase in the covalent radius. So 77 to 118. So there is a large increase, and after that there is only a slight increase in the covalent radius of all the other elements. So carbon 77 picometers, then silicon 118, and then 122, then 140, 146. So there is a considerable increase in covalent radius from carbon to silicon. There is a large increase in the covalent radius one can observe, and thereafter silicon to lead only a small increase in radius is observed. And This is due to the presence of completely filled due to the presence of completely filled d and f orbitals in heavier members. And here from this electronic configuration, this thing we can see d and f orbitals. Even from here, the vacant d orbitals will start coming, and here this element contains d orbitals. And what we know, d and f orbitals, if electrons go into d and f orbitals, the screening effect for those electrons are very less. But what we see, other things, other change that happens is that one proton also goes into the nucleus, and the screening effect of added electrons in d and f orbitals are very small. And so because of this, we see an effective increase in the effective nuclear charge, and because of that, we don't see much effective and much larger increase in the atomic radius in these elements. And so 118 for silicon, then germanium 122, only 4 units increase, 4 picometer, and then 122 to 140, and then 142, 146 from tin to lead. Look into the ionization enthalpy. Ionization enthalpy, we know it's highest for the carbon. So if one can ask, covalent radius, it's lowest for carbon and highest for the lead. And the ionization enthalpy, we see it's highest for carbon, and we know carbon is a non-metallic element, and its non-metallic property is highest in this. So as we go down, the metallic property increases, and there is a general trend that we know from the periodic property. And out of these elements, carbon and silicons, they are non-metals. There are many. So carbon is non-metal. From silicon and germanium, they are semiconductor. So this is non-conductor, this is semiconductor, and this here to tin to lead, they are both are metal. So let's see the ionization enthalpy for carbon is highest, then after the silicon, then we see germanium, then tin, and from the tin we see slight increase in ionization enthalpy for lead. So in general, the ionization enthalpy decreases down the group. One can say in general, ionization enthalpy decreases down the group. Only exception we see from tin to lead. So a small decrease in ionization enthalpy for silicon to germanium. Silicon to germanium, we see there is very small increase in this is a consequence of poor shielding effect of intervening d and f orbitals and increase in size of the atoms. The same reason that I cited for a small increase in covalent radius, you can cite same reasons for the small increase in ionization enthalpy. And now what we see, ionization enthalpy, whenever I am talking about it, means we are trying to ionize electrons, we are trying to remove electrons. The covalent radius, since these electrons, other than some metals, most of the compounds they form, they are covalent compounds. So that's why covalent radius is important to be studied about that trend. So now let's look into the electronegativity. Electronegativity, as we know, the carbon and electronegativity usually in the periodic trends we have seen, usually it decreases. What we see in the carbon family in particularly, uh, we are magnifying this all the things. So the carbon, its electronegativity is although highest in the group, and after that we see the electronegativity value is almost same. So for silicon, germanium, tin on the Pauli scale, we see the value is 1.8, 1.8, 1.8, and for lead it is slightly increased to 1.9. So one can consider from silicon to lead, almost there is no change in the electronegativity value. And due to a small size, elements of this group are slightly more electronegative than group 13 elements. This is what we should understand, because group 13 and group 2 and group 1, these elements are left to this group 14 elements in the periodic table among the representative elements of the main group elements. And so these elements, the elements of group 14, have slightly higher electronegativity than the corresponding elements of the group 13. So the carbon, if you consider the electronegativity of boron and carbon, if you compare, you'll see electronegativity of carbon is more than electronegativity of boron. And here we will compare electronegativity of aluminum and silicon. Silicon's electronegativity is more than electronegativity of aluminum. And similarly, you can see the similar thing can have similar comparison in the same period. The Electronegativity values for elements from silicon to lead are almost the same, and that we see from these values. Now let's see this table. So properties and all these things are summarized. So properties, the elements carbon, silicon, germanium, tin and lead, the elements are there, and the properties, the atomic number, what we know, the atomic number of carbon is 6, silicon is 14, germanium is 32, tin is 50 and lead is 82. So what we see from germanium to lead, you see the increase is of the 50. So if you just add this 50, 32 plus 50, 82 is the atomic number of lead. And see from here 14 plus 100, if you add 50 into 2, these are 2 plus 14 plus 100, so 114 will be the atomic number of flerovium. Anyway, that is not our focus. So atomic masses for the carbon, we know mass number 12 around, so the atomic mass will be 12.01. And this atomic mass, one can say the molar mass, because this atomic mass is shown here in gram per mole. Usually average atomic mass we represent in AMU. So in AMU 12.01 AMU would be average atomic mass, and here the atomic mass that is shown in gram per mole, this is the molar mass of this element. Molar mass of carbon is shown in gram per mole, and the silicon is around 28, germanium 72.6, and 73 mass number you can roughly remember, or 72.5 one can say, 72.5 is more close. And the tin, so 119 approximately, and this lead 207 mass number. Electronic configuration of all the elements we have seen. So 2s2 2p 2 for carbon with the core of helium and the neon and all these things that we have seen. The covalent radius, the values we have seen, an increase, larger increase from carbon to silicon, and then only a slight increase thereafter that we have seen. The ionic radius, when we talk about, so ionic radius, we see the carbon doesn't form ionic compound, being a non-metal, it doesn't form any an ionic compound. So carbon doesn't show any kind of ionic compound, so our ionic radius of +4 or +2. So there could be two types of ionic compounds of group 14 elements, where the metal or the element is in +4 oxidation state or +2 oxidation state. Carbon doesn't form any of such compounds, ionic compounds, because it is a non-metallic element. Now we see the ionic compound of in +4 oxidation state, means when the ion is in the +4 form, we see it starts with the silicon, and we know SiO4 is being formed. Yes, also similar kind of things. So from ionic compounds, if you see ionic radius from 40 is for the silicon, and ionic radius is also increasing. So from silicon, germanium, tin and lead, we see there is a continuous increase in the ionic radius for plus in the +4 oxidation state, or in the +4 form. So ionic radius for in or +2 form, and the picometer is shown here 73, 118 and 119 for germanium, tin and lead. So in +2 state also the ionic radius is increasing, but what we see in the +2 state, even silicon doesn't form ionic compound, and that's why ionic radius for silicon in +2 oxidation state is not shown. The ionization enthalpies in kilojoule per mole is shown here. The first ionization enthalpy for any element that we know it's lowest, and thereafter the ionization enthalpy, subsequent ionization enthalpy is always increases, and from the second ionization enthalpy is more than first ionization enthalpy. Third ionization enthalpy is more than second ionization enthalpy, or fourth ionization enthalpy is more than the third ionization enthalpy for any element. And as we know, there are 4 elements in the valence shell. So for all the 4, so 4 electrons in the valence shell. So all the 4 electrons can be removed with the proper, if the energy is provided. And however, the difficulty of removing electrons increases, difficulty of removing electrons increases, you need to provide more and more energy to remove electrons. And as we know, carbon is a non-metallic element. Non-metallic, it is a non-metallic element because it doesn't want to lose its electron. It doesn't want to give its electron. It doesn't have any free electron, and that's why it's electronegative element. One can say electronegative element. That's why it don't like to give its electron. And being metallic character is something related to something, and being electrons in the free form and the conduction band as a free electron. So non-metals also do not have electrons in the conduction band to be considered as a free electron, because the conduction band, the gap between conduction and valence band is very high, and this kind of things we have seen very briefly in the chapter when I taught chemical bonding, the metallic bonding, the conduction band, valence band. I have explained slightly in the brief. And so, what we see, the ionization enthalpy for carbon is highest in the positive, and positive means energy is to be provided, to be given to remove electrons from this element, and we see first ionization enthalpy, it decreases and then it increases from tin to lead. The only exception that we see here. And similarly, what we see, the second ionization enthalpy also it is decreasing. One can see here, and then from tin to lead it increases. And the similar trend we can see for every cases. Every cases we see first, second, third, and fourth. All the ionization enthalpy we see the same trend everywhere. However, if you add all the ionization enthalpies of all the value of all the ionization enthalpies, one can see this value is significantly higher. This is also significantly higher, and based on that, one can understand that exciting all these electrons or removing these electrons from carbon and silicon, it is very difficult, extremely difficult. For carbon, it is almost impossible. Now the electronegativity value we have seen for the carbon is 2.5, and then silicon, germanium and tin it is 1.8, and for lead it is 1.9. So we see from here to here it is almost same. The density, density, what we see, the density of carbon and then silicon it decreases, and thereafter from the silicon to tin the density increases. But the question is why the density from carbon to silicon decreases. So the reason is here. If you remember the covalent radius, I think even so reported here, the covalent radius, we see there is a significant increase in the radius. However, we don't see much increase in the mass number from carbon to silicon. So carbon to silicon, the mass number you see from 12 to 28. So the only 16 units increase in the mass number is seen. However, in other cases, we see a larger increase in the mass number and a very small increase in the covalent radius or the atomic volume. So the volume, and that's why, as we know, the density is mass divided by volume. So there is not much increase in the mass from carbon to silicon. However, there is a larger increase in the radius, and that's why mass divided by volume increases from carbon to silicon. However, later on we see a correspondingly high increase in the mass number or the average atomic mass, and there's very slight increase in the covalent radius, and that is volume, and that is why the density increases consequently after silicon. So slowly there we see from silicon there is a continuous increase in density. So the silicon is the element, group 40 is the element which is having lowest density in the group. And the melting point, so melting point as we see it decreases up to here, up to the tin, and from tin, as we see the similar trend for the ionization enthalpy, we see tin to lead, the melting point also increases. The boiling point, if you look, the boiling point it decreases, and it decreases continuously up to the lead. The electrical resistivity, and resistivity one can know that it's the opposite to conductivity, and so as the carbon is not metal, even the silicon and germanium are they are kind of metal wire, they are semiconductor, and other tin and lead are metal. So the resistivity for the carbon would be highest being non-metal, and that we see resistivity is 10 to the power 4 to 10 to the power minus 10 to the power 16, 10 to the power 14 to 10 to the power 16 in this order. And so the conductivity will be 1 divided by this, and so you can see the conductivity will be that 10 to the power minus 14 to 10 to the power minus 16 in this order it will be observed. However, the resistivity of silicon and germanium is not very high, although it is high, but it is not very high. It is between metal and non-metal, and so it's a semiconductor or the metal wire. and the resistivity of tin and lead is very low, and tin and lead the resistivity is low means the conductivity is high, and that is why tin and lead are metals. Now let's look into the physical properties. All the group 14 elements are solids, so they exist in the solid state in the nature. Whether carbon, silicon, germanium, tin, lead, they are all solids. Carbon and silicon are non-metals. That is what I have said earlier. Particularly carbon, the germanium is a metal wide, and germanium is a metal wide that you can see here. Also, if you look at the periodic table, that see the boron, silicon, germanium, silicon. Although this book explicitly writes silicon as non-metal, your NCERT says, but what would I say? And based on the common sense, that the silicon is also a metal wire and the conductivity of semiconductor, so it's not a non-metal. So mostly we can have a bit correction here, and this statement, the sentence I have taken from the NCERT book, and that's why I thought to keep it there. But ideally, one should not write carbon and silicon. Mostly one can write carbon is a non-metal, germanium, what I silicon, and germanium are metal wire, whereas tin and lead are soft metals with low melting points. So the tin and lead are soft metals with low melting points, and low melting point we have seen here. For the metals, being the melting point 505 and 600 is a low melting point. And because while you can see the melting points of other elements, they are very high for other elements. For the tin and lead being they are metals and they are soft metals being having low melting points, and the silicon and germanium you should remember as being metal wire or the semiconductor. Not silicon one should not remember as a non-metal, although NCERT book says it's a non-metal. The carbon is a non-metal in this entire group. The melting points and boiling points of group 14 elements are much higher than those of corresponding elements of group 30, and this trend we should remember. The melting point and boiling points of group 14 elements are higher than the corresponding elements of group 13. Corresponding elements in the comparison of the elements of the same period means if you want to compare the melting point of carbon, you should compare it with the melting point of boron, because boron is in the same period. And if you want to compare melting point of silicon, you should compare melting point of silicon with the melting point of aluminium. So the melting point of silicon is much more than melting point of aluminium. And similarly, one can have similar things one can say. Now let's look into the chemical properties. First of all, we will see the oxidation states and trends in chemical reactivity. The common oxidation, the one thing that I have seen, the highest oxidation state these elements can show is +4, and the lowest oxidation state as -4. And the common oxidation state exhibited by these elements are most common are +4 and +2. It doesn't mean carbon that they will not exist in other oxidation state. They are means +4 and +2 are most common oxidation state. Although we see carbon also exist in -4 oxidation state, like -4, -3, -2. If you look at the CH4, the electronegativity of carbon is more than that of hydrogen, and there the carbon in the CH4, the methane, carbon is in -4 oxidation state. The hydrocarbons we see the carbon usually in the hydrocarbons is in the carbon is in negative oxidation state. In the ethane molecule, the ethane C2H6, in ethane we see the oxidation state of carbon is -4. If it is ethene C2H4, in ethene oxidation state of carbon is -2. Acetylene oxidation state one can consider oxidation state of carbon at -1. And so these elements can show other oxidation states as well. However, the most common are +4 and +2, and also Carbon also exhibits negative oxidation state, as I said, -4, -3, -2, -1, all oxidation states is those, and the zero oxidation state carbon can also show because carbon can exist in the elemental state as well. And so the diamond, graphite, these allotropes of carbon. You see there is only carbon-carbon bond, and so the oxidation state of carbon in graphite or diamond, all these elements, even the coal or the fullerene, oxidation state of carbon is zero. The heavier members, the tendency to show +2 oxidation state increases, and as we know, the compounds in +4 oxidation state are generally covalent in nature. And why compounds of +4 oxidation state in +4 oxidation state are covalent? So two reasons one can cite. First reason is removing all the 4 electrons that we saw the ionization enthalpy is very high. So removing all the electrons to form ionic compounds or to form metal 4 plus ions is very difficult, because this much energy we may not get by uh, releasing energy, because once the bond formation happens, ionic bond formation happens, the lattice energy will be released. So the lattice energy equal to the lattice energy will be released in the formation of the ionic compound, but that energy will not exceed the sum of energies of sum of ionization energies. It means that energy, the ionization enthalpy is very high. One thing, another reason could be, one can say, because this element is in +4 oxidation state, and +4 oxidation state, there you can also apply Fajan's rule. And so the Fajan's rule, +4 oxidation state, charge to size ratio will be very high, charge to radius ratio will be very high. It means these elements in +4 any element in the +4 oxidation state will have more tendency to pull shared pair of electrons towards itself, and that is why the electron cloud of the anion will be deformed more and more, and it will so deformed that the electron cloud of anion will come almost in the middle between the two atoms, two bonded atoms, and so compounds in +4 oxidation state are generally covalent in nature. Some exceptions are also there, and exceptions are particularly essential for in heavier members. The tendency to show +2 oxidation state increases, and that is because of the inert pair effect. We know as the atomic sizes increases or the number of electrons increases, what we see, the penetration of the number of cells increases, penetration power of s orbital increases, and as the penetration power of s orbitals increases, or s orbitals, even the outermost cell s orbitals will be more closer to the nucleus, and so removing those electrons will become even more difficult, and that is why heavier elements show a greater tendency to be in +2 oxidation state. And so germanium, tin, and lead, we see this tendency to show to be available to be present in +2 oxidation state increases in this order. So the lead has shows the +2 oxidation state will be most stable for the lead, and then tin, and then germanium. So in heavier members, the tendency to show +2 oxidation state increases in the sequence germanium, tin to lead, and this is due to inability of NH2 electrons of valence shell to participate in bonding, which we call the inert pair effect, and the reason I have explained. The relative stability of these two oxidation states vary down the group, and that's the relative stability of this two oxidation states means +4 and +2 oxidation states. These are two oxidation states. It varies down the group. Carbon and silicon generally show +4 oxidation state, and so the carbon and silicon mostly they exist in +4 oxidation state. However, as we see in the heavier metals, the lead mostly show +2 oxidation state. So germanium form stable compounds in +4 state, and only a few compounds in +2 state. What we saw, the carbon and germanium, carbon and silicon generally do not form any compound in +4 oxidation state, as a +2 oxidation state. They mostly form, carbon and silicon mostly form compounds in +4 oxidation state. They do not form compound in +2 oxidation state. Germanium can form compounds in +2 oxidation state, but those compounds are not stable. So germanium, for even for germanium, compounds in +4 oxidation state are stable. Tin forms compound in both oxidation state. Tin and lead also forms compound in both +2 and +4 oxidation state. However, tin in +2 stage is a reducing agent. Reducing agent means what? Even for tin, +2 oxidation state is less stable than the +4 oxidation state, and that is why if the tin is in +2 oxidation state like SnCl2, so it will increase its oxidation state and will form SnCl4, and SnCl4 to form SnCl4 to increase its oxidation state, tin will have to remove its electrons, and those electrons, if it is removing, it will be added to something else, and that compound will be reduced, and that is why tin in +2 oxidation state is a reducing agent. And why it is reducing agent? I have explained. Let me again explain it. Because relative stability of tin in +4 oxidation state is little higher than +2 oxidation state, and that is why tin in +2 oxidation state is a reducing agent. However, we see just opposite thing for the lead. So lead is most stable in +2 oxidation state, and therefore lead is a strong oxidizing agent in +4 oxidation state. So if lead is in +4 oxidation state, it means, and this +4 oxidation state is not stable for lead, rather +2 is the stable one, and so lead will accept electrons, it will remove electrons from something else, not from itself. It will accept electrons, gain electrons from some other material, and two electrons from some other materials in process to become from +2 from +4. So it will become +2 from +4, and that's why it takes two electrons from some other material, and that is why if it is taking electron, it is oxidizing that material, and that is why lead is a oxidizing agent and a strong oxidizing agent in +4 oxidation state. So up to tin, what we see, +4 oxidation state is most stable. We see for the carbon and silicon only +4 exists, +2 doesn't exist. For germanium and tin we see, and even for lead, +2 +4 both exist. However, for germanium and tin, +4 is more stable, and that for the lead +2 is more stable. Germanium and tin +4 is more stable, and for lead it is +2 which is more stable. So in tetravalent state means all the electrons are occupied in the bonding, the covalent bonding, and the example is the carbon tetrachloride CCl4. We see the tetravalent means the four covalent bonding. In tetravalent state, the number of electrons around the central atom in a molecule, the example CCl4 is 8, and this is what we call the electron precise compounds. The electron precise compound is the electrons in the valence shell of the central atom are exactly 8. Such compounds are called electron precise compounds. And molecules will be called electron precise molecules. So in the tetravalent state, the number of electrons around the central atom in a molecule is 8, and that is 8 we see because the carbon shares one electron with one chlorine, and so two electrons for one bond, and there are such four bonds, four CCl bonds. Each bond contains two electrons, so 2 into 4, 8 electrons will be in the valence shell. In tetravalent state, the so being electron precise molecules that in the tetravalent state, they are normally not expected to act as electron acceptor or electron donor species because they are electron precise, and since they are electron precise, they do not like accepting or donating electrons. Although carbon cannot exceed its covalency more than 4, and that is what is important point, because the tetravalent state silicon also can form tetravalent compounds in tetravalent state, and the tetravalent state, it means it also has 8 electrons in its valence shell. However, if you compare carbon in the tetravalent state and silicon in the tetravalent state, will be one difference. Carbon doesn't have a vacant d orbital, however silicon does have a vacant d orbital, and so since because the presence of vacant d orbital, silicon can expand its octet, and so silicon can have more than 8 electrons in its valence shell, and that expanded octet. So although carbon cannot exceed its covalency more than 4, because 4 covalency means it already had uh, 84 into 2 covalency. Each bond has 2 electrons, so 8 electrons, and since it doesn't have vacant d orbital, so it cannot expand its octet. But the other elements of the group can do so, means they can expand their octet because of the presence of vacant d orbitals in them. And due to this, halides of heavier group 14 elements undergo hydrolysis and have tendency to form complexes by accepting electron pairs from donor species. And so, because these elements, heavier elements, means other than carbon, from silicon onwards, silicon, germanium, tin, lead, and so these species have vacant d orbitals, so they can accept in those vacant d orbitals, they can accept a lone pair of electrons from the electron rich species, for example, water, halides, and so on. And so one can see the expanded octet, the compounds to form compounds having more than 8 electrons into the valence shell, and the example is SiF6 2 minus. And SiF6 2 minus, what we see, it is actually SiF4 plus extra 2F minus, and two fluoride ions will actually, each fluoride ion will put one pair of electrons in the one of the vacant d orbitals, and so two d orbitals will also be occupied here in the octahedral geometry, and this is SiF4 2 minus anion. Similarly, one can have GeCl2 minus 6 GCl6 2 minus. We are not showing SiCl6 2 minus. You can see here. So G, this is because the silicon cannot have 6 electrons will be here. If 6 chloride will be here. SiCl6 doesn't exist, is what I wanted to say. SiCl6 2 minus is because carbon is much larger. Sorry, chloride is much larger anion than the fluoride, and so silicon cannot accommodate around it 6 larger size chloride ions. So, but germanium, which is larger in size than the silicon, can accommodate 6 chloride ions around it. So, GeCl6 2 minus can exist, and similarly SNOH whole 6 2 this compound exists, whereas the hybridization of central atom is sp3d2. However, in the tetravalent state, we see the hybridization of the central atom will be sp3, because the 4 covalent bonds means the sp3 hybridization. 6 covalent bonds means sp3d2 hybridization, and d2 hybridization means 2d orbitals are also taking part in the hybridization, and those orbitals will be empty, and they can accommodate, they can accept 2 electrons from the bases, and these bases could be fluoride, chloride, or hydroxyl ion. Now let's look into the reactivity towards oxygen, the activity of group 14 elements towards oxygen, and what we know, the all members form oxides. So all the members of group 14 elements, they form oxides. They form mainly two types of oxide, that is, the one is the monooxide and another is dioxide of formula MO and MO2 respectively, and the example of carbon monoxide CO and CO2 carbon dioxide, that we know, very common example. So the all the elements that can form MO and MO2 type of oxides. SiO only exists at a higher temperature. Oxides in higher oxidation state of elements are generally more acidic than those in lower oxidation states. The oxides CO2, SiO2, GO2 are acidic, whereas SnO2 and PbO2 are amphoteric in nature. So, what does it mean? The CO2. CO2 is what? And SiO2 and GO2 are acidic. So, the plus 4 oxidation states, oxides of germanium are acidic, whereas tin and lead are amphoteric. Means tin dioxide and lead dioxide, SnO2, PbO2, they are amphoteric in nature, means they can react with both acid as well as bases. However, the dioxides of carbon, silicon, and germanium, the CO2, SiO2, and GO2, they are acidic in nature. Among monooxides, carbon monoxide is neutral, GeO is distinctly acidic, so CO is neutral, and GeO, germanium monoxide, is distinctly acidic, and the tin monoxide, and lead monoxides are amphoteric. So what we see, whether it is dioxide or monooxide, the oxides of tin and lead are amphoteric in nature. One can see here, and oxides of up to germanium oxides of germanium are always acidic, whether it is GeO2 or GeO. However, monooxide of carbon is neutral, and here the dioxide of carbon and silicon both are also acidic in nature. Let's take this question. Select the members of group 14 that forms the most acidic dioxide. So most acidic dioxide, but we know the acidic dioxide as we go down the group, the metallic character decreases, and as the non-metallic character increases as you go up the group, and that is why carbon will form the dioxide, and if the non-metal forms the metallic oxides are more acidic in nature, and all of the elements all the elements of group 14, the carbon has highest non-metallic character, and that is why carbon oxide is most acidic in nature. The commonly found plus 2 is commonly found in plus 2 oxidation state, and this example we have seen for lead because of the inert pair effect. Plus 2 oxidation state of lead is most stable, not plus 4, and that is why lead in plus 4 is a very strong oxidizing agent. This thing we have seen. And the third one, used as a semiconductor, and used as a semiconductor, as said earlier, the silicon and germanium being metal wired, they are semiconductor, and their resistivity value we also have seen it is 50, and so the conductivity will be in the order of the semiconductor. Let's see the reactivity towards water. So the carbon, silicon, and germanium are not affected by water. So the carbon, silicon, and germanium, they do not react with water. Tin decomposes steam to form dioxide and dihydrogen gas. So tin react with water to form dihydrogen, the hydrogen gas plus tin dioxide. So Sn plus 2H2O on heating it gives decomposes steam on the heating it decomposes. So tin decomposes means it splits its hydrolyzed water and in the form of SnO2 plus 2H2O. So the hydrogen gas will be removed, and this is the property of metals that we know. The highly electropositive metal. So tin is an electropositive metal. It can split water into water, and so the hydrogen gas will be evolving during the reaction. The Sn plus 2H2O gives SnO2 plus 2H2O. Lead is unaffected by water because of the protective oxide film formation. So lead forms a protective oxide film, which is a PbO formation. However, lead react with the moist air, but lead can react with the moist air. Means lead can react with, if the oxygen is also there, so lead can react with water. In that case, water in presence of oxygen and converted to PbOH twice. And so if the so Pb plus, one can write H2 water plus oxygen, and you will see a formation of PbOH twice. The reactivity towards the halogen, one can also, and so reactivity particularly, let's see this thing. So group 14 elements form highlights of formula MX2 and MX4. So plus in plus 2 and plus 4 oxidation state, both oxidation states are available or the accessible, not the better word. So plus 2 and plus 4 oxidation states, both are accessible for halides of group 14, and so halides can exist in MX2 and MX4 form, where X could be fluorine, chlorine, bromine, and iodine. Except carbon, all other members react directly with halogen under suitable suitable conditions to make halides, and so other than carbon, if this is not carbon, so other members, from silicon, germanium, tin, and lead, they react with the halogen to form MX4 under suitable conditions, different conditions for different things. So most of the MX4 are covalent in nature. The exception is this thing I have also explained earlier, and they are covalent in nature for two reasons that I have them: ionization potential, and another reason that I have explained is the Pajan's rule. And the exceptions are SnF4, PbF4 are ionic in nature. So SnF4 and PbF4 are ionic, and this is because one can see the Pajan's rule Sn plus 4, and the fluoride is a smallest size anion, and being a smallest size anion, its ion polarization will be difficult because anion is very small in size, and so these compounds MX4 plus 14 and lead means SnF4 and PbF4 are ionic in nature. Other than that, what we see MX4 compounds are mostly covalent in nature. The central metal atom in these halides undergo sp3 hybridization, and one can very easily understand sp3 hybridization here. Because four bonds, and this I think I have said four sigma bonds, and because of the four sigma bonds, we can say that sp3 hybridization will be there, and molecules are tetrahedral in shape because sp3 hybridization, and there is no lone pair of electrons on the central atom, and that is why these molecules will be tetrahedral in shape. Means they will have perfect shape, and that perfect shape for sp3 hybridization is a tetrahedral shape. PbI4 does not exist because PbI and this PbI4 compound, this compound doesn't exist. And the example, the reason one can see PbI bond, the ionic bond formation. The PbI bond will be with a covalent bond. Even iodine is much larger in size, and even for the ionic bond, one can say you see that because of the larger ionic radius of iodine, what we see the lattice energy will be very low, and because lattice energy will be low for PbI4, so the Pb will not form ionic compound, and since Pbi bonds, the covalent bonds are also weaker because of larger covalent radius of iodine and lead both. So PbI4 doesn't exist because PbI bond initially formed during the reaction does not release enough energy to unpair six s2 electrons and excite them to higher orbitals to have four unpaired electrons around lead atom. This is the same thing I explained in different words. And so how the energy will be, how bonds are formed. So initially the what we consider for the just a thing, although that doesn't happen in reality in the same order. So what are the same sequence? So what does it mean? What is written there, that the electronic configuration of the outermost shell for the lead will be 6s2 and 6p2. So the two electrons, those two electrons, they will be in the two p orbitals. They will first make bonds with the two iodine atoms, and once the two PBI bonds will be formed, the energy will be released. And if that energy is enough to excite six s2 electrons, so what will happen? These six s2 electrons, one of the electron will also get excited and will go to one vacant p orbital, because p orbitals can accommodate three electrons in the singly occupied basis. So p orbitals have three orbitals, of p subshell has three orbitals, and a p subshell of lead contains only two electrons, and those electrons, according to Ohm's rule, will be in two different orbitals. So even though it has one vacant p orbital, so if the excitation of 6s2 electron happens, the one of the electrons may jump to 6p electrons. However, for that one need energy, and this energy will be obtained by the formation of PbI bond, two PbI bonds. But these PbI bonds, being iodine very larger in size, are not so strong, and two electrons, that energy is not released, that much energy is not released to excite one electron from 6s to 6p orbitals, and that is why PbI4 doesn't exist. A similar thing I have another way, another viewpoint I have also explained. Whether it's the ionic compounds, one can say ionic compounds, the crystal energy or the lattice energy will be very low, and for the covalent compounds, one can say this PbI bond is not strong. So for such bonds, the such PbI4 will not be stable in such oxidation state. The heavier members germanium to lead are able to make halides of formula MX2, the stability, this thing we know, stability of dihalides increases down the group, and the stability of dihalide, because of the inert pair effect, it increases down the group, and so dihalides can exist only from germanium to lead. Tin and carbon do not form dihalides, as I have we have seen earlier, because carbon and silicon are not stable in +2 oxidation state, and the dihalides these elements are in +2 oxidation state. So the +2 MX2 formation for carbon and silicon is this type of compounds and do not exist. But for the germanium to lead, such compounds can be formed, but their stability increases down the group. The only PbX2 is the stable member. Other members GeX2 and SnX2 are very less stable. Their stability is less, but their stability increases down the group. The stability of dihalides increases down the group. GX4 is thermally and chemically more stable than GX2, whereas PbX2 is more stable than PbX4. I have already explained the reason. Except CCl4, other tetrachlorides are easily hydrolyzed by water because of the presence of vacant d orbitals in the central atom. It can accommodate the lone pair of electrons from oxygen atom of water molecules in it, other than CCl4, because carbon doesn't have vacant d orbitals. But after the carbon, silicon does have vacant d orbitals. There are many all other elements also do have vacant d orbitals. So the tetrachlorides, other elements, what will happen? The lone pair water can put one of its lone pair into the vacant d orbital of the central atom. If suppose SiCl4, one of the examples one can consider. And so when the one of the vacant d orbitals, water can put its lone pair of electrons, and later on those bonds, the O and Si bonds becomes stronger, because affinity of silicon with oxygen is just more than that the chlorine, and that and so one what we see that the one OH bond will be breaks one OH bond of that is of the water molecule. The mechanism we'll see a bit later. And the silicon, one SiCl bond will also break. So the formation of HCl will be there. It means the except, again I'll read this, except CCl4, other tetrachlorides are easily hydrolyzed by water. And why they will be hydrolyzed? Because they have vacant d orbitals, and CCl4 will not be hydrolyzed because it doesn't contain doesn't have vacant d orbitals. And so now these vacant d orbitals will behave as electron acceptor, and if this will initially in the first step itself, it will accept lone pair from water molecule, and now the water molecule will come and see it forms a coordinate bond, and coordination bond, a coordination bond it will form, and later on we will see further changes. So for example, SiCl4 undergoes hydrolysis by initially accepting lone pair of electrons from water molecules in d orbitals of silicon, finally leading to formation of SiOH4. The mechanism is, for the first step itself is shown here. This is SiCl4 in the tetrahedral geometry, because it is sp3 hybridized, silicon is sp3 hybridized plus water molecule, and this water molecule will now one of the lone pairs. Suppose this lone pair, it can push into one of the vacant d orbitals of the silicon, and so the silicon now will be in the pentavalent geometry, the SiCl4 and OH2. But the OH2, what we see, the OH, the H and O bond, one of the OH bond will cleave, and the one of the SiCl bond will also be broken, and so HCl bond will be forming, and what we see, the HCl will be forming, and here that is why HCl is released, and the SiCl 3OH formation happens, and then subsequent step this can happen 3 times in the subsequent steps we see finally the formation of SiOH4, which is called silicic acid. So this is silicic acid SiOH4. Well, we will see this question and other important points in the next lecture. I'll stop here because the time is over.